Inequalities. The thing politicians hate, but mathematicians love. Let's take a look at some inequalities problems. Starting off with probably something you're probably familiar with, the trivial inequality. And this is quite frankly trivial. It just says that perfect squares are always greater than or equal to 0, which makes sense because negative times negative is going to be positive. That's why it's called trivial inequality. But despite being trivial, it's actually super useful. For example, completing the square, if we complete the square, we can find the maximum and minimum values. If you can, let's do that really quickly. So we complete the square, get x plus b over 2a squared, and we then, what else do? We have plus c minus b squared over 4a. I just completed the square quickly. So take a look is that because this is always greater than or equal to 0, the minimum value, if a is positive, then the minimum value occurs when this is 0. It occurs when b is negative b over 2a, because that makes it 0, and the minimum is this. If a is less than 0, then now this thing is always going to be negative. So now this is now the maximum. And this is useful. Simple, yet powerful. Okay, so that was kind of like the core thing you have to know. There's a few simple examples here you can practice with in the book, but I'm not going to be covering any examples using the trivial inequality. Now I'm going to talk about some more nuanced inequalities, probably ones you're not familiar with because they're not as trivial. Starting off with AM-GM inequality. It says that the arithmetic mean of two numbers is greater than or equal to the geometric mean of the two numbers. For example, 3 plus 4 divided, let's take a different example actually. 4 plus 9 divided by 2, which is 6.5, is greater than or equal to 4 times 9, because that's 6. And this is always true for positive or non-negative numbers A and B. And why is this true? The proof is super simple. A plus B greater than 2 root AB. Now we square. We get a plus b squared greater than or equal to 4ab. And now take a look. We can rewrite this as a squared plus b squared plus 2ab minus 4ab is greater than or equal to 0. But take a look. That's just a minus b squared. And this is true because of trivial inequality. So even though it's trivial, it's really so useful. And a nice corollary of this is x plus 1 over x. By the AM-GM inequality, we have that this is greater than this, which is 1. So x plus 1 over x is 2, and that's the minimum. Cool corollary. So what is AM-GM useful for? Well, if you ever make it to Olympiads, then there's often inequalities problems that ask for proofs using these things. But for AMC and AME purposes, the main things we're going to want to do is use AM-GM to find the minimum value of a plus b. Because what AM-GM tells us is it allows us to find the minimum value for sums and maximum value for products. So let's just take a really, really simple example just to begin. This is not even on here. What is the maximum value of x minus 2 over x? The AM-GM is useful for maximizing products and minimizing sums. In this case, maximizing a product. Well, we just write AM-GM for this. We have this is going to be less than or equal to x plus 2 minus x over 2, which is 1. So x times 2 minus x is just going to be less than 1 squared, which is 1. Super simple problem. Oh, another thing I forgot to mention about AM-GM is that when is this equal? It's equal when A is equal to B. So in this case, the equality or maximum would happen for this expression will happen when x equals 1. Just a simple example to get things started, and I'm not sure why this is so squished, This problem was not supposed to be inside of a corollary. I'll fix that later. But now let's take a look at this AMC problem. AMC, AMCA. What is this expression here? So we've got a bunch of non-negative integers. Their sum is 12. We're trying to maximize this thingy. Now, if you did the algebraic manipulation chapter, you're probably familiar with these types of expansions here. Now, this is a very classic factorization and pattern you should recognize. In fact, I think something like this came on the USA GMO this year, like a very similar factorization for number 1. And it's this factorization right over here. We expand this all out, we get AMC plus AM plus MC plus AC plus A plus B plus C plus 1. Now, this is something super useful you should know. And you might realize that if it's just 2 variables, it's just AM plus A plus M plus 1. But for 3 variables, it's kind of a little bit more. You got the product, you got the product of 2 terms, you got the sum, and you got 1. And this generalizes to more as well. So super helpful factorization. Should know it if you don't already. And that's so useful, as you can see here. Because now, we're trying to find the maximum value for this. But we already know this thingy is 13. This whole thing is 13. Why? Because A plus M plus C is 12. So we add 1, 13. So let's just subtract this from both sides. You get this minus 13. Aha! So now all we have to do is maximize this term, and we maximize this quantity here. How should we maximize this term? Remember, AM-GM is useful for maximizing products and minimizing sum. We're trying to maximize a product. AM-GM is the way to go. And actually, I just realized we haven't even covered AM-GM for n variables. So this is just for 2 variables. But it turns out we can generalize. If we take the arithmetic mean of any n numbers, it's going to be greater than or equal to the geometric mean for n numbers. Basically, the geometric mean is just the nth root of the product of all of the numbers. So the average of the n numbers greater than or equal to the nth root of the product of all the numbers. So now let's maximize this using AM-GM. We got the cube root of A plus 1, M plus 1, C plus 1. And that's less than A plus 1 plus M plus 1 plus C plus 1 all over 3, which is 5. So we cube both sides, we get that this thingy is less than or equal to 125. So this quantity has a maximum of 125. And therefore, the maximum of AMC plus AM plus MC plus AC is 112. Because this thingy had a maximum of 5 cubed, and we subtracted 13 to get 112. Where we had this, and then we cube both sides, we get A plus 1, M plus 1, C plus 1, less than or equal to 125. And when does equality occur? It occurs when all of these 3 things are equal, i.e., these things are all going to be equal, and because the sum is 12, that means A, M, C are all also going to be equal. They're all going to be 4. So the maximum value of this occurs when A, M, and C are all equal. And the maximum is 112. Okay, yeah, and then, I just talked about here how it relates to this. The minimum of the sums here is just n times this. The maximum of the product here is this quantity here, which is basically the same thing we're doing with our AM-GM. Okay, now we're going to talk about weighted EM-GM. And rather than presenting this to you with a scary formula, which you will probably be scared of, or maybe not, but let's just take a look at an example, because really it's intuitive if you think about it. okay, find the maximum value of this. You might be like, maximizing products. AM-GM, for sure. So then you try AM-GM. Okay, you're like x times x times x times 4 minus x. The fourth root of all of this is less than or equal to x plus x plus x plus 4 minus x all over 4. And this is equal to, well, 4 plus 2x by 4. The maximum value of something in terms of x? That's not what we really wanted, did we? We don't want a maximum in terms of x. We want a maximum number. So this is not going to work. Why didn't it work? Because the sum, in our previous case, our sum was super nice. Our sum was something that was constant. Here, our sum is not constant. But are we just going to give up on this problem and be like, the sum is not constant, this is too difficult? We're going to do some clever tricks here. And we're going to make this sum a constant. What are we going to do? Well, what happens when we make each of these terms x over 3? Then this sum is just 4. Which would give us a maximum value of 1 for that. Okay, but we're not trying to find the maximum value of x over 3 to the third power times 4 minus x, right? If we wanted to find the maximum value of this, then this would work. But what we've just done is we found the maximum value of this quantity to be 1, which would imply the maximum value of this to also be 1. But we don't want to do that. We want to maximize this. We know the maximum of this. We're trying to find the maximum of this. Pause the video, think about this for some time. This is just 27 times this. So the maximum value of this is just 27. Do you get it? Basically, we had x plus x plus x plus 4 minus x here originally, which didn't give us a nice sum. But what we did is we just like, okay, let's just divide out by 3 to all of these terms, and then we'll get a nice sum, which is constant. And then we can just multiply by 27 back later. No big deal. Boom. Got a maximum. Super cool trick. And that's really all this is saying. Weighted AM-GM. Just basically, instead of having A2, we just have A2 plus A2 C2 times. But instead of C2 being an integer, it can be any real. Okay, now let's take a look at another problem. This one is from the AMC 12. This is not, just so you know, inequalities is not something that really comes on the AMC 10, but it does come on the AMC 12 and AMI as well. And answer completely hidden. Okay, we want to maximize this quantity. Again, we've got a product. We know how to maximize products. AM-GM, boom. 2 to the t minus 3t times t, well, divided by 4 to the t. So let's maybe worry about the 4 to the, or yeah, let's just divide out by 2 to the t to each term. So instead of dealing with the 4 to the t in the denominator, which is kind of annoying, have this. Okay, so now we've got a product. We know how to maximize products. AM-GM. This is less than or equal to 1 minus 3 times t over 2 to the t. All of this plus t over 2 to the t. This divided by 2. That's not good. This sum is now 1 minus 2 times t over 2 to the t. But again, we don't want a maximum value in terms of t. We want a maximum number. So this sum, we need to somehow make it constant. So pause the video, try and think about this. What can we do to make this sum constant? What we can do is multiply by 3 to this term. 3 times this. Why? Because now our sum is a constant. So now, based on this inequality, we have that this is now going to be equal to 1/2. That's it. And now we square both sides. We get that just this part. I'm going to copy it. Unfortunately, you probably won't have a copy and paste tool during the actual 90-10 contest. We have this is going to have a maximum of 1/4. But then we're like, uh-oh, we multiplied by 3 here. Now what are we going to do? We just divide by 3. It's that simple. Boom. And this can become 1/12. Our final answer is just 1/12. This is like one of the most cool concepts in my opinion. When I first learned about this, I was like, wow. Just multiply and divide, and then weighted AM-GM is just so powerful, really. Okay, now let's take a look at Cauchy-Schwarz inequality. And again, in this general format, it looks super scary, but I promise you it's not that complicated. Okay, so let's just take a look at an example of Cauchy-Schwarz rather than trying to explain it from this complicated notation. So let's say we have something like a squared plus b squared. Let's say we're trying to this. What Cauchy-Schwarz tells us is that, well, let's move it a bit down, I think. Cauchy-Schwarz will tell us that this is less than or equal to a cubed plus b cubed plus c cubed times a cubed plus b cubed plus c cubed. What are we really doing here? I don't know a good place to put this. Let's just try it here. Oh, that's a little bit annoying. Okay. So Cauchy will tell us this is true. Now, why? Basically, all we have to do is take this term, we multiply them together to get a to the 6th. We take their square root here. And then this term, this term, we multiply them together, take their square root. This term, we multiply them together, take their square root. So we can also rewrite it like this. We're basically kind of averaging out the terms. We're taking the geometric mean of this term, and we're making it this term. Geometric mean of this term, and making it this term. Geometric mean, and then this term. And for example, we can also rewrite it. So let's say we can do this for anything. Let's say we had 6, 8, and then we had like some giant values, 12, 2, and then maybe we can even have a 0. So let's just say 1, like that. Again, same thing. A squared, a to the 12. Their product is a to the 14. Square root of that, a to the 7. B to the 6, b squared. Product b to the 8th, square root b to the 4. C to the 8th, 1. Product c to the 8th, square root c to the 4. So all we're really doing is, and now we can look at the general form maybe, should make more sense, is, this is kind of written in reverse, maybe I'll change that later, is we take this term, we take the square root, we put it here. And the product of these things is going to be bigger than this. And that's always going to be true. And a cool corollary of this is T2's lemma. Basically, this is just saying that, let's say we have a to the 4 plus b to the 6 plus c to the 8 times 1 plus 1 plus. And we're trying to find out what we can do is we can just say, okay, let's multiply this by 1 plus 1 plus 1 using Cauchy-Schwarz. This is greater than or equal to a squared plus b cubed plus c to the 4 squared. Right? We just take the square root of this. And that's really all this is saying. That's in this fancy notation. We're just basically doing Cauchy-Schwarz, but instead of using that, we have 1 plus 1 plus 1 as our multiplier, rather than some other term that includes a's and b's. Let's now take a look at this problem from the AMC 12 that uses Cauchy-Schwarz. Let a, b, and c be real numbers such that their sum is 2 and the sum of squares is 12. What's the difference between the max and min value of c? So one thing that Cauchy-Schwarz could tell us is that this is greater than or equal to this. Because a squared times 1 is a squared. The square root of that is a. Similarly, this and this. And if you ever forget which direction this Cauchy inequality sign, it's always the side that has two distinct terms is going to be greater than or equal to the sign that has just one term squared. Let's try and use, is this even useful? I mean, we already know this. We get 12 times 3 is greater than or equal to 2 squared. 36 is greater than or equal to 4. That's so useful. I mean, who knew that? So clearly this application of Cauchy-Schwarz is not very useful. But the thing is, we're kind of looking specifically at C itself. So what should we do? Let's try and isolate C a little bit, maybe. So let's maybe make A plus B on one side, because A and B are kind of symmetric. We're not really asked about any of them. So we have A plus B is 2 minus C. And A squared plus B squared is 12 minus C squared. And now, what if we use Cauchy-Schwarz with just these two terms? Then that might give us some values for C. That might give us some bounds for C based on that. Let's do that. Cauchy-Schwarz in action. So we multiply, and we're going to use T2's lemma here, which is just like I mentioned earlier, kind of the same thing. We multiply by 1 plus 1. And the reason being is now on the right hand, on the other side, we get A plus B squared. Because A squared, 1, square root A. B squared, 1, square root B. We have this is greater than this. And the reason we wanted 1 plus 1 is now 1 and A squared will become an A here. And B squared and 1 will give a B here. And now we can write something purely in terms of C. So until now we had A, B, C. But now Cauchy-Schwarz allows us to eliminate A and B out of the picture completely. We get 12 minus C squared. 2 times this is greater than or equal to 2 minus C squared. Now we've got a one variable inequality. Gotten rid of A and B. That's really the main motivation here. Over here, we subtract C squared, and now we just forget about A and B. Okay, so now from here it's not that difficult really. That was the tricky part of the problem. Now we just expand, and now this is a really simple quadratic style inequality, which I'm sure you've solved in algebra 1 before, is less than 0. And to find the difference between the maximum and minimum values is just going to be the roots of this quadratic. And you can actually do some clever Vieta stuff as well. Why not? You can solve the quadratic the boring way. But just for some, I'm pretty sure this is factorable. Yeah, it's factorable, but let's practice using Vietas. So R plus S is 4/3. RS is negative 20/3. So this is we're trying to find R minus S. Whatever the magnitude of this is, absolute value. So now what we do is, this is a standard Vieta trick. We do r plus s squared. We subtract 4rs, and then this would give us r minus s squared, right? Because r squared plus s squared plus 2rs, r squared plus s squared minus 2rs. And now we get 16 over 9 plus 80 thirds equals this, which is what, 256 over 9. So r minus s, for the absolute value of that, is 16 thirds. And that's the answer for this problem, 16 thirds. So the key idea here is complicated with a bunch of these variables. Cauchy-Schwarz regularly is useless. But we want to get rid of a and b. We don't want to deal with these inequalities. So we make it like 2 minus c and 12 minus c squared. Now that gives us a way to make our inequality in terms of just c. And that's a simple algebra 1 style inequality, which we can solve the boring way using factoring or using Vietas, which I think is just more interesting. Okay, and just to summarize some of our tricks for inequalities, we have Cauchy, weighted AM-GM, AM-GM, and trivial inequality. Don't overlook this one. It's more useful than you might imagine. And also something you want to do in these maximization minimization problems is actually verify that your equality case actually holds. To verify that, okay, sure, because sometimes what might happen is you have something like this is less than or equal to this, but there may not actually be a point where these are equal. So your maximum bound therefore doesn't work. So it's a good idea just to check, okay, in the equality case for this, what must be true? And in Cauchy-Schwarz, equality happens when the ratio of this term to this term, this term to this term, they're all the same. That's when there's equality. Okay, and that's it for this video. But in the next video, we're going to take a look at logarithms. This is literally the heart of AMC 12. There's so many logarithm problems. So if you're taking the AMC 12, you're going to want to check out this next video on logarithms.